very much to the organization for giving me the opportunity to give this talk, and I'm sorry that I couldn't make it, but we're teaching in Leeds this week, and post-COVID, it would be very difficult to tell the students that we wouldn't be there. So I just spoke about AGN, so probably I will nick some slides from tomorrow and show that to the students on Friday as well. So, I'd like to talk about massive evolved stars today. In particular, some of the results that we got with gravity. I will mostly talk about one post-red supergiant called the Freitag Nebula. And at the end of the talk, I'd like to say something about the latest results that we got from another one that's called IRC plus 10 for 20. And these are all the co-authors we have on the papers that report on these results. So the Freitag Nebula, I gave a little bit of an introduction on post-red supergiants and massive star evolution. And then I will go talk about the inner regions of the circumstellar material of this object, Freitag, and the outer material. And after that, I'm going to show that despite being at 4 kiloparsecs away, IC 10 for 20, we actually found some changes on the sky over the period of less than 10 years. So where are we in the HR diagram? Here I only show the HR diagram from about 100,000 solar luminosities, and I got some usual suspects. I've got the red supergiants. I've got the luminous blue variables here, some B bracket E supergiants, and a couple of wolf-rayet stars. And these are all the results of post-main sequence evolution of very massive stars. And at the end of the day, they will explode as a supernova. But yeah, these wolf-rayet stars and LBVs, they came from often, I thought to come from the red supergiant branch. And there's a whole class of objects that are between those two. The states of evolution is actually similar to the post-HB stars we looked yesterday, but now for more massive objects. There's a lot of yellow hypergiants here, with the luminosities of a few 100,000 solar luminosities. And what we don't know really is whether these objects came from the main sequence to the right, or sorry, what did I say? Or came from the post-red supergiant phase to the left. So we know they must be evolved because otherwise they wouldn't be there. But the states and evolutions are often very difficult to assess. But a few of these yellow hypergiants have evidence for really a lot of dust around them, which indicates a post-red supergiant phase of mass loss. Okay, and because these guys are on the way to become either an LBV or a supernova, it's quite an important stage in the life of a star. Okay, and one of those is an iris source, and it's dubbed the Freitag Nebula. And here's my postage stamp for this guy. In Herschel data, you can see a huge ring that's about 50 arc seconds. And if you zoom in with Vizier data at arc second resolution, we're talking about 10 micron here, we find evidence of multiple shells already at these very small scales. And when you play a little bit with the Lecoq color, you can see why Eric Lagerdijk thought it was the Freitag Nebula. It's an A-type star. We managed to establish that from optical spectra we took. It's about 1 kiloparsec. It's optically bright-ish, and it's incredibly reddened. So there's a lot of interstellar material, which makes the object really intrinsically very bright already. And what I find quite amazing is it's in the top 30 of the brightest iris sources, and the iris catalog came out 40 years ago, but it was hardly studied in the meantime. I think it took about Lagerdijk looking at it in 2011 that we started to understand that this is a really very bright object in the post-red supergiant phase of evolution. Now then, where do we come in? Well, for the inner regions, we decided to study this object with gravity to see what's really going on there. And let me first show you the spectrum here. We've got bracket gamma emissions or hydrogen recombination lines, typically what you would think. There's some neutral sodium lines and singly ionized magnesium. So these are lines that you would expect to arise in more cooler material, while the bracket gamma, if it is traced in the ionized gas, would be from a much smaller region. And we got quite a good UV coverage, so we're lucky enough to do some image reconstruction, which you find on the right-hand side. So it's it's a busy picture. The grayscale is really the unresolved 2-micron source. It is the star. The size scales turn out to be incredibly consistent with the luminosity. The blue roundish material is in fact the sodium emission line region, while the reddish, more extended material is the bracket gamma line emitting region. So it's nice, of course, to talk about the geometries here, but I think here I want to highlight the size scales because it's quite puzzling when you think about it, is that a neutral line from sodium is coming from a smaller region than a line like bracket gamma. And indeed, we have seen this sodium doublet emission in quite a lot of evolved stars. Basically, we've got 100% hit rate for yellow hypergiants. It's not really common for other types of objects, but with spatial information, we can actually constrain and understand what's going on. It's really odd to have ionized gas, if you indeed think that bracket gamma is coming from ionized gas, outside the neutral region. But when we got John Black on board and he did some thinking, he said, well, you don't have to have hydrogen recombination lines from recombination. If I just have collisional excitation of an atom and you go to a higher energy level and then you drop down, you can get that emission. So what he did is basically just got a very simple, for him, not for me, LTE 2-zone model, just a higher density in the middle, a slightly a higher temperature, and a lower density outside and a slightly lower density. And he could reproduce the emission line strength of the sodium lines, of the magnesium lines, and of the bracket gamma lines, and indeed even mimic a little bit of absorption for the outer parts. So I think that's a major, well, you might think it's technical detail, but it's a major understanding, at least for as far as I can see, of how these cooler objects actually behave, because we've got quite a few F and A type stars with a lot of emission, and we often think it's due to recombination, but instead we can explain it with collisional excitation. A little bit about the outer parts. We also thought it would be nice to actually try to model the SED and break the degeneracy again by modeling the spectral energy distribution by adding spatial information. And the Vizier data reveal actually 3 shells. So it's fantastic. You've got an SED, you find actually from the radio profiles 3 shells. So we decided to use the 2-dust program to fit the SED and find some information. And that's what we did. We managed to fit the SED from the optical, including the extinction. And here, this is the hotter inner shell, the middle shell, and the outer shell. And if I'm looking at the total contribution of the 3 of them, then we can actually get a very nice fit to both the SED and to the radial profiles. So this allowed us to actually not only work out the SED itself, but we learned that we actually need 3 shells to do so. And we find that we've got 3 distinct shells. We can work out the kinematic ages of the shells and the mass loss rates. It turns out that the middle shell is the biggest one with 10 to the minus 4 solar masses, but the inner shell is only 10 to the minus 7 solar masses per year. But the last shell, the inner shell that I'm talking about, was only 30 years ago that the material was ejected. So this leads us to believe that this is actually mass loss that is happening during the yellow hypergiant phase as well, and not only due to the red supergiant phase. Okay, so I think it's this type of information about intermittent mass loss that is telling us a lot about the evolution of massive stars. Just like with young stars, where the accretion of material is not smooth anymore over a long period of time, but we think that's actually happening. This episodic accretion for the evolved stars, we also start to understand that there's actually episodic mass loss, and it's data like this that help. Now, talking about episodic mass loss, let me now talk a little bit about IRC plus 20, which is not a post-red supergiant. Almost a similar story as the fried egg. We managed to get gravity data of it. The UV coverage was not good enough to do image reconstruction. Instead, we used the P-Moirad. I've heard this before. I still don't know how to pronounce it. To model the images. As you can find, the sodium emission, which is quite strong, 30% continue, is a compact source, slightly larger than the star, while the bracket gamma emission is indeed much larger. And in a way, it looks like it's a detached shell of this object. Okay, we haven't been able to do the modeling yet, but it looks like we've got a slightly similar situation again, that we've got the sodium emission very close. The work that I'm mentioning here now is just submitted for publication. And what I wanted to share today with you is that 10 years ago, we got amber data of the same object. That was at a higher spectral resolution. We didn't have P. Moria then, but Willem Jan de Wit, a very clever man, used his own geometric models and found exactly the same geometry as I just showed you on the previous slide. But he actually managed to look at it in velocity intervals as well. So we've got a full circle, if you like, that's approaching us, and something that's not very full is receding. So perhaps some light might be absorbed. It's looking the other way around. The brightest here is on the right-hand side, the brightest here is on the left-hand side, but that's basically because we mixed up east and west. Sorry. And what Willem Jan came up with his ad hoc model was that we might have a kind of a bipolar flow with a cone that's moving away from the star. And what we find now is in these 7 years that the size scale of this ring, the shell, on the sky expanded from 4.2 milliarc seconds to about 5.8 milliarc seconds.
You have 2 minutes left.
That's fantastic. Thank you. I think that's exactly what I need. At 4 kiloparsec, that size scale change corresponds to 2.5 kilometers per second, which is of course weird if I tell you that the approaching material is at Doppler shifted velocities of -40, -50 kilometers per second, and the redshifted material is at about 50, 60 kilometers per second. But it's fully consistent with the idea that if I've got a bipolar flow where the ring is moving towards us with at a very high speed, but if the opening angle is very small, then I can have a very large radial velocity, but the tangential velocity will of course be much smaller. So we find about 2.5 kilometers per second, which actually allows us now to constrain the opening angle of this bipolar flow. Okay, so I think that's we still need to digest really what it all means, but I find it very interesting, at least for the sake of this talk. 2 supergiants, post-red supergiants. One seems to be spherical, and the other one seems to be bipolar. So there's a lot of variety even in the evolution of massive evolved stars. So our next step is to understand more about the most recent mass loss episodes. Here I show you some CRIRIS plus spectroscopy already, where we're looking at bracket alpha and the fundamental CO transitions at 4.6 micron. And we're going to combine this with our upcoming Matisse data to really pin this down also to break the degeneracy, both spectra with velocity information and the images. And my conclusions, I think it's fair to say that the mass loss from the Friday Nebula is not steady at all. In the last 130 years, we had 3 burps of mass loss already, and most likely the last one definitely during the supergiant phase. We also start understanding now the emission mechanisms, what leads to the bracket gamma and the sodium emission around the inner material close to the star, which helps us understanding the mass loss process itself as well. And finally, I think it's fair to say that I couldn't even dream of it even 10 years ago, that we would be able to see something moving on the sky in the space of only 7 years when it's 4 kiloparsec away. Okay, that's what I wanted to share with you. Happy to take any questions.
Questions? Online question. So we have a question from Keishi Onaka. What's the mass lost in the 3 outbursts in 130 years?
Yeah, there was a slide I threw out because of the time. Where are we? The hot inner shell was 30 years ago, 6 × 10⁻⁷. The medium one is 100 years ago, 10 to the minus 3-ish almost, and the outer shell 120 years, 5 times 10 to the minus 5. And these are gas mass loss rates.
Question? No question? So thanks again, René.
No worries, thank you.